this video, we're going to look at a second very specific probability model known as the binomial distribution. And it is, as I said, a very specific distribution for a certain type of scenario. So let's examine what conditions have to be met in that scenario. So we use a binomial model when we want to know the number of x successes and in a fixed number of n trials. So in order to use it, again, it has to be a Bernoulli trial, meaning we use BINS. We're going to use the BINS acronym to help us remember the conditions. And think binomial begins with bin, so binomial BINS. So binary is B, meaning you have to have a success and a failure. Independence has to be met where the outcome of one event is not impacting the outcome of another. Now, if independence is violated, we can still look at that 10% condition, where if your sample is less than 10% of the population, it's okay to proceed. Another way of saying that is little n, the sample size, is less than 1/10 of capital N, the population size. Now, the n in BINS means that we have a fixed number of n trials. Okay, so you got to be given that part. That's really one of our major differences between binomial and geometric. And then the S is still, you can think same success, or the probability of a success stays the same for S. Okay. So again, we're looking at Bernoulli trials, and a binomial model is used when we want to model the number of X successes in a fixed number of N trials. So as I've just mentioned, we use a binomial model when we want to model the number of X successes in a fixed number of trials. So again, X is our number of successes. Let me change the size of that. Number of successes. And N is the number of trials. And P is the probability of a success. The binomial distribution formula is given to you on your AP formula sheet. And as always, if you forget what parameters you have to mention to get full credit, it's listed on the formula sheet. Your parameter is N, which is your number of trials, and P is the probability of a success. Okay, so here is the formula, and you should notice this part now. We talked about this. That's a combination from N, choose X, times probability of that many successes to the X power times the probability of a failure to the number of N minus X, which we'll put this into actual context. Now our expected value, again, will be our mean, which you'd find by doing N times P, and our standard deviation is given here, N times P times the probability of a failure. Example 1, recall the Tiger Woods example from the text. Suppose a cereal manufacturer puts pictures of famous athletes on cards in boxes of cereal in hopes of increasing sales. 20% of the boxes contain pictures of Tiger Woods. Suppose you buy 5 boxes of cereal. What is the probability that you get exactly 2 pictures of Tiger Woods? So, how I know that this is a binomial model? Well, it's saying, what's the probability of getting 2 successes in 5 trials? Okay, probability of getting 2 in 5 fixed trials. I should check BINS. So the B, it's binary. A success would be a box contains Tiger Woods, a failure would be no tiger. The I for independence, because we draw without replacement, we check the 10% condition, and 5 is less than 10% of all boxes. N is we need a fixed number of trials, so we're saying that N is fixed at 5. And S, we need the probability of same success. The probability is 0.2 for each box. Okay. I could also say that 1 minus P then would be the probability of a failure would be 0.8. Alrighty, so how do we do this? We are being asked, what is the probability that you get exactly 2 And as I think about how to logically do this, well, I want exactly 2 successes out of 5. So that means 2 successes and 3 failures. So a lot of times kids would just think, okay, so that's 0.2. I've got 2 of them, so 0.2 squared. 2 successes, 3 failures. Make that 0.8. 3 failures. And multiply that together. However, think about this. That only accounts for one possible arrangement. So maybe the first 2 boxes you pull are successes, but what if it's the first and the third? Or the first and the fourth, or the first and the fifth? Or the second and the third, the second and the fourth, or the second and the fifth? Are you getting where I'm going with this? There's a lot of different ways this could play out. So we have to account for all the different combinations. So what we're really saying is the number of combinations, we need to multiply that. So from 5, choose 2 times 0.2 squared times 0.8 cubed. Now, if you look on your AP formula sheet, how is this written on the formula sheet? From 5, we're choosing 2 times the probability of a success to the second power times the probability of a failure, 0.8. And this would be 3 failures to the third power. Now we just in our warm-up did a combination from 5, choose 2. You can do that on your graphing calculator, again by math, probability, arrow over to that and choose option 3. And this is the way it pops up on the calculator, and it will output. There are 10 different ways that it could occur. So 0.2 squared, 0.8 cubed, toss that in the calculator, and that probability is 0.2048. Now, maybe you're wondering, is this function completely in the graphing calculator? Like, can I avoid showing all of my math altogether? Well, yep, you can. I'm big on understanding where it comes from. I like that better, but you can. There's a binomial distribution model. It's hidden in second vars again, and you're going to go to option A. There's a binomial PDF and CDF. If you're looking at a specific value, which we are here because we want to know that we get exactly 2 pictures of Tiger Woods, not less than or equal to 2 pictures. We're going to go with Binomial PDF. So I'll write out my calculator talk here. Please find it on your calculator, and you'll see it will ask you for the number of trials. So I'm going to say n equals 5. The value of p, probability of success, is 0.20. And then it also asks you for your random variable fixed at 2. Okay, and the other good thing is for full credit on the AP exam, if you look back at that formula, you have to always specify the value of n and p, so you also have it written here to make sure you got it somewhere in your problem. Hit enter, and lo and behold, I get 0.2048. So there's a 20.48% chance of getting exactly 2 pictures of Tiger Woods in 5 boxes. Let's do one more. It says, the communications monitoring company Postini has reported that 91% of email messages are spam. Suppose your inbox contains 25 messages. What are the mean and standard deviation of the number of real messages you expect to find in your inbox? And what's the probability that you'll only find 1 or 2? Okay, so I see a fixed number of trials. That fixed number of 25 signals to my mind that I am looking at a binomial model. So let's prove it first by checking our conditions. So this is binary. A success I'm going to define as a real message, and a failure would be getting spam. As far as independence, I'm going to say that my messages arrive independently. One is not impacting the other from another company, etc. N, I have a fixed number of trials. And S, probability of the same success. Let's say P equals 0.09 for each message as they arrive randomly. So I've checked my conditions, so now I'm stating I will model with a binomial model of, I'm going to just state my 2 parameters right away so I don't forget about them from my formula sheet. I know I need to state P equals 0.09 with n equals 25 trials. All right, so I've made sure I'll get full credit for stating what model I'm using and my parameters, and I showed that I checked my conditions. And now I'm going to do two things here. Part A, what are the mean and standard deviation? Okay, so the mean, I'm going to go to my formula sheet. My mean mu of x is equal to n times p. That's pretty easy math, so 25 times 0.09 is 2.25. And then I'm going to find my standard deviation, which is n times p times the probability of a failure. So the number of trials times successes times failures. So 25 times 0.09 times 0.91, and then we take the square root of that, is approximately 1.43. I will put that into context in a sentence in just a second, but let's first answer part B. So what's the probability that you find only one or two real messages? So this would be the same as probability that x is 1 plus the probability that x is equal to 2. So mathematically, that would be equivalent to a combination from 25. We are selecting just one success, so all the different ways that occur, times 0.09 to the first power, and then we would have 24 failures, so 0.91 to the 24th. Again, you can just plug that into the formula. I'm just showing you how to logically think it through. And we're going to add that to, now, what's the probability from 25 having two successes? So we got to look at all those combinations, figure out how many there are. 0.09 to the second, two successes, 0.91, and that would be 23 failures. Okay, so you're going to have to do from 25, choose one on the calculator. You can actually just type this all in on the calculator. To do that, just to show you, rather than me pulling up my graphing calculator, this is what you would do. You would use this function, and you would just do times 0.09 to the first times 0.91 to the 24th, plus go to math, probability. Option 3, again, combination from 25, choose 2 times 0.09 to the second times 0.91 to the 23rd. Okay, so take a second, actually practice doing that, and I get 0.5117. Okay, now you could also do this going Binomial Pdf. You need to say N25 P 0.09 X equal to 1, and then you're going to add that to Binomial Pdf because you're doing two scenarios here, and we're adding them together. Probability that your random variable is 1 or 2. Binomial Pdf, N equals 25, P equals 0.09, and X equals 2. Okay, when I do that, I also get 0.5117. So just to also mention, sometimes kids say, well, can I use Binomial CDF, the cumulative density function? You would still have to do this in 2 steps, because Binomial CDF would calculate your probability of getting no real messages, 1 and 2. So it's at 2 and fewer, so that's going to include 0, 1, and 2 in your answer. So if you did cumulative Binomial CDF, you would then still have to subtract a Binomial PDF at 0. So, equal amount of work is what I'm really saying. So let's put both parts A and B into a conclusion now. So my conclusion here is that among 25 emails, I expect to find an average of 2.25 real messages with a standard deviation of 1.43 messages. And then for part B, there is just over a 51% chance that 1 or 2 of my 25 emails will be real messages. Please don't skip the step of putting things in context. This class is so much about communicating effectively. So conditions, use bins, state your model with your parameters, show your calculations, and in your calculations, if you use calculator talk, it's fine, but make sure you define your parameters within it. And then your conclusion.